All right, let's quickly sketch most of our favorite functions. These are kind of the tools in our toolbox for modeling situations or graphs with formulas. You probably don't need much help on linear functions. They can increase, they can decrease, they can stay steady, but that's pretty boring. Quadratics or parabolas, they can be smiley, they can be frowny. Polynomials actually are pretty rare in applied modeling practice. They can look like that. They can look like that. Can they look like this? Nope. They pretty much either end up increasing forever or decreasing forever. So they can't just have a horizontal asymptote or a gentle curve at the end. There's square root of x, which usually looks like this. E to the x. Now this one you should practice drawing, and e to the negative x. These are pretty important ones, so if don't wait for me to draw it, just pause the video and sketch it yourself. That tells the neurons in your brain, hey, I need to know this stuff, so it's better for learning. All right, you done? So e to the x looks like this. E to the negative x looks like that. Logs, try sketching a log real quick. They look like this. They go to infinity and they go to minus infinity down that way. You can have an upside down log, and sometimes Excel will offer to fit one for you if you use a trend line. But logs in general are actually not very common in applied modeling. I think I've seen a log model actually be useful maybe a half dozen times in my 300-year career as a math person. So even if a trend line in Excel for log fits pretty well, I wouldn't really trust it usually. Sine and cosine look basically the same. I guess the question is, do you start high and go low? Do you start in the middle and go up? So we'll write down those questions. So do you start high and decrease? Do you start in the middle and increase? Or do you start low and increase? That would be a negative cosine. Logistic is probably one you haven't heard of before. It's also called an S-shaped curve, and it has horizontal asymptotes at either end. So I'm going to draw kind of an asymptote that the curve never quite gets to, and another asymptote that the curve never quite gets to. Or you can have a decreasing logistic that starts near an upper horizontal asymptote and gets near a lower one. How about e to the x times sine 20x and e to the negative x times sine 20x and e to the positive x times sine 20x? Try to imagine what those are going to look like. You ready? So sine 20x is going to be oscillating fairly rapidly, and e to the negative x is going to be a decreasing amplitude. So it's going to be initially large amplitude that kind of peters out. And this one is going to be exponentially increasing amplitude. So it's going to increase more and more like that. So we could call this one a decaying oscillation. And this one, you could call it a growing oscillation. And another name for this kind of phenomenon is often resonance. If you've got a kid on a swing and every time they come back toward you, you give them a little extra push to get them going farther, and your pushing is timed exactly with how they're swinging, they're going to be swinging more and more and more, and you can tell I'm a good parent, right? It's fun. All right. Surge curves are another important kind of function. Sometimes they start out kind of linearly from the origin and then grow and then decay back towards y equals 0. Sometimes they have a little bit of an upswing first and then decay back towards 0. The general form is t to the p times e to the minus t, and this p is an adjustable parameter. It's usually above 1, but not always. So these start at the origin. If you plot them, you'll see that this formula does have values back for negative t values, but we usually just ignore those. Just start with positive t or 0t. All right, and where have we seen surge curves before? When we were doing pharmacokinetics and tracking medicines moving through the body and stuff, we saw a lot of surge curves. And then the last one, it's exponential behavior, but it's not quite exponential growth, and it's not exponential decay. I call it exponential approach to a horizontal asymptote. So let's say you have an asymptote like that, and you start here at the origin, and you increase. So it's exponential, it's increasing, but it's not exponential growth. So this is a curve like 1 minus e to the minus t. So that's important in a lot of probability kind of stuff. So that's our survey of commonly useful functions in modeling with formulas and functions. And now let's turn back to the bouncing baby fun.